Welcome to another episode of Rudy's Electronics Lab. And before I'm going on holidays, I found a bit more time to make one more episode. And I wanted to continue on the series of oscilloscope comparisons that I've already been working on in the past. And specifically to look at them in terms of what they support for math functions. And math functions have been with us already for a fairly long time on oscilloscopes. I got two oscilloscopes standing right here, a Tektronix 350 megahertz, I think. It has addition, it has invert, so you can also do subtraction. Also my Hamex scope, I think I bought it when I was about 15 years old and it still functions perfectly. It's a very nice state, can do exactly the same thing. So mathematics have already been with us on oscilloscope live for a long time. And for a good reason. There are a lot of type of tasks that we're facing where we need to do some sometimes simple and sometimes advanced type of mathematics. So today I want to go and look into the mathematic function of the three oscilloscopes that I've been looking at before. And the topics that I'm going to deal with today is, first I want to talk a little bit of mass channels, but also the complexity of these mass channels. Then I will be investigating and doing testing on all the three devices, how they do things. And then I want to go also into the question of how they deal with division by zero situation. That is something I'm particularly interested in, and that is something that does pop up quite a lot, I think, in measurements. I said three scopes, but actually four. I'm going to add a scope to the equation. I'm going to add here this PicoScope. It's a series 3000 oscilloscope. And I haven't been including it in my original series. Actually, I didn't have the time or the resources for that, but it is rather interesting in a number of ways. And I'm bringing it in today because when it comes to math, we see some very specific, interesting things with the PicoScope. So we're going to look at four oscilloscopes today. Now, if we merely would look at the numbers in terms of specifications, we would see how many channels, mathematic channels a device has. We would see how many different mathematic functions you can define. We could see whether there are like filters among them, high pass filter, low pass filter, band pass filter, and band stop filters. We can see whether the device can do tracking of parameters like frequency or pulse width, and whether it has formula editors. So putting this everything down just to mere numbers, I think, does not reflect the real diversity that we find across devices in order to do something. So we'll actually be finding that some oscilloscope can deal with some types of challenges, others can deal with other types of challenges, only a few can deal with all of them. So it really depends on the specific implementation, much less so than on the sheer numbers of function or numbers of channels. So that will also be a bit the focus of my episode today. Now let me illustrate that with a formula that I've been using, I think, in one of my recent episodes. Is the one for reactive power in power analysis. C equals to the square root of A squared minus B squared. Now, three devices that I'm looking at today can do it, but they do it in a rather different way. On the Roden and Schwarz RTB, you can do it, but you need to use all the mass channels, and each of them are just going to do one single function and building on each other's output. A bit of complicated to do it, but it is possible if required. The Siglent SDS2000x Plus scope basically has a formula editor, and you could quite straightforwardly input that formula there yourself. And finally, the PicoScope is even nicer. It got a specific built-in function for that called reactive power, and you just say which are the two channels, and that's all. So they're very different in the way that you achieve a particular task. And without pretending I'm covering all the different type of things you can do in measurement or pretending that one is really better than the other, I just want to give you a grasp of the diversity and whether devices are able or not to deal with certain function by giving an example of like 5 different type of calculators. Well, 6 it is. And we see the formula that I just presented to you. 3 of the devices can do it, the Keysight is not able to do it. Actually, we'll see that the Keysight is relatively limited. Add up 4 harmonic waveforms. I'll be looking at in some of the examples later today. All the devices except the Keysight can do that. Calculate reactive power. That is the result of 3 different formulas that we need to use together. The Siglent can do it. The PicoScope can do it, actually in 2 different ways. But the Roden and Schwarz isn't able to do that. Then again, taking 4 different analog channels and all put like a high pass filter on them with a defined 3 dB cutoff point, etc. The Rode and Schwartz can do that, and the PicoScope, but not the Siglent. If we, for example, would take 4 analog channels and we would like to create a little digital to analog converter, so we take one value times 1, another value times 2, another value times 4, another value times 8, and then create an output value. The Siglent can do that, but the RTB cannot. We don't have enough channels to do it. PicoScope can also do it. Oh, quite interesting, none of them are able to deal with digital channels on their mathematics. I'm a bit disappointed by that, but that goes for all the devices. While again, tracking the frequency of an analog channel, that's something that the Rode and Schwartz can do and the PicoScope, but the Siglent can't do. So I'm not trying to say one device better than the other, but they're all very different in terms of what type of things they can do, and we'll dig into the details of that. Perhaps most importantly, I try to create an overview document where for these devices I go into in detail of each the measurement function that is there and how it's implemented as a regular function or as or a formula editor type of functionality. And I made this kind of for myself if I'm dealing with type of tasks to figure out which device that I'm going to use for a particular type of challenge, because they're quite complementary to each other, I would say. Okay, let's start with the mass function of the RTB. So I've created a sine waveform on channel 1. On channel 2 we got also a sine waveform of 3 times the frequency, so the first odd harmonic. And we're going to look at some mass functions. So here we see basically 5 mass channels, and each of them we can choose a function. So there's only one single function here, no formula, but one single function. So a function can have one single input like the inverse, but the function can also have 2 inputs. So let's take addition. I'm going to add channel 1 and channel 2, and since we're adding 2 voltages, I'm going to leave the unit here on voltage. The channel is turned on, and what we get to see as a result is basically a something that looks a little bit more like a block wave. And of course we should, because if we would add infinitive number of higher odd harmonics to it, we would get a perfect block wave. That's what theory dictates. Actually, we can try to use the mass function to do exactly that. I got a 3rd channel here, and we got the 5th harmonic coming in here. I'm going back to the mass function here. I'm going to create a 2nd mass channel, and so I'm going to take channel 3 and I'm going to add that to the result of the 1st mass function. So I'm adding up all 3 of them. I'm going to go back here and I'm going to activate that. I forgot to activate it. You can also do it from here. And what we see, we got resulting extra tracer, and this one is a little bit more flatter at the top. So it's a little bit more already like a block than the addition of only 2 sine waves was. So here we basically see how we can build up formulas basically using multiple single steps. But whether that works or not for a given situation, well, that depends how complex the formula is and how many operations you need to do. So the great thing about this scope is that you can have 5 relatively simple channels being shown as traces all at the same time. So 5 is quite a lot, but for each of them we can do mostly a single operation only. The fact that the RTB can only do one single operation for a mass channel does not mean that these operations are always simple. We got a couple of simple ones like addition, subtraction, etc. But we also got rather sophisticated ones like tracking and high pass filters and low pass filters. Let me demonstrate one of them to you now. Here I prepared a signal, and this signal varies in pulse width. This could be a signal, for example, driving a modern type of motor. And if we zoom in on this signal, we would see here that the pulse width is gradually increasing, and then it comes to a point suddenly where there's a really huge pulse width. It's going to be high for a significant amount of time here. So I'm going to try a mass function here that would track the pulse width. So in order to do that, I will go to math. I'll select tracking the pulse width. I'll select channel 1 as input. And what we get to see here, and I'll make it a little bit bigger. Yeah, we see the pulse width here increasing. We can even make it a little bit bigger here. Also almost sinusoid. And then for one moment the pulse width is going to be really, really big here. So this is a really nice functionality. And we can also look, for example, at the duty cycle. And other functionalities are frequency, track frequency and track period, but now I'm going to check the duty cycle. And here we see that the duty cycle of that signal increases also over time in an almost sinusoidal type of wave. So we really do have advanced type of function, at least some of them. Moving to the SDS, I created the same two signals here, and moving basically to the mask channel here, we can also get it from there, from the menu. We basically we got two mask channels. So I'm going to use mask channel number 1 here. I'm going to start operation. I can set its function and a couple of other things like labels. So when we select the function, we get to a menu here. We got basic, we got arithmetic frequency analysis algebra, and we got a formula editor. Now anything in basic is also present in the other categories here. So we'll just look at the other categories. So here we got arithmetic things, so we got addition, so we would have two source channels here. And like with the RTB, basically we can select another channel, but we can also select the result of another math function basically as an input to the other one of the two actually we got here. So we got a number of basic functionalities here. We got also averaging and ARES, an enhancement of number of bits here. And let's look at averaging. If we do that, then we actually get here the available settings, like for example the number of averages we would like here. Now, as already discussed elsewhere in my my videos, it's nice to have averaging, but for me averaging should not be in a math menu, it should be in a channel itself, because that way it could be used for all type of analysis function or whatever. And once you make it part of a math function, it's really limited, because the math function are not an input to analysis things like in the analysis menu. So I think that is a major limitation that they put it on this spot. I mean, the averaging is there and the ARES, but it's in the wrong spot of the scope, I would see. Identity is just the value in itself. I don't know exactly why you need that, but apparently it holds a function. Max hold and min hold, for example, hold the maximum value in multiple sweeps. So we got little key tips here, which are quite useful. Frequency analysis, that basically just makes us start the FFT function. I don't know why we need that here in the math things, but anyway, we can also start up FFT in another way, but it's here. We got algebra type of functions, so integrals, derivatives, and that type of thing, square roots, a certain number of functions. And the interesting stuff really starts happening when we go to the formula editor. And the formula editor also has a number of functions. Some of them overlap with what we just saw in the regular menus. Some of them don't. And in a separate document that I am making available, I made a complete list of all the functions of this scope and other scopes, so we can see where is what, including what is in the formula editor, what is in the regular ones, and what is in both. And of course, the nice thing here in the formula editor, we can make really advanced type of formula. So it basically will be here, for example, that we can take the square root of a signal which is in itself, for example, C3 times C4. And as you see, it was in red until I finished the full formula, so it's checking basically that I got the whole thing correct in terms of the number of parentheses and the number of parameters. But you can also do magic, I would say, because now we are in function number 1, and I can say function number 1 is actually function number 1 divided by a constant of 2. And he accepts this. And this is of course forbidden. This is a recursive formula. This never should be allowed. So I think this is really something still to be addressed by Siglent, that forbidden type of formulas really should be identified and not allowed, because before you know, actually you make mistakes and you make recursive type of things or other type of things there. yeah, a bunch of functionalities. You can combine them all together into a very complex type of formula. That makes this, this scope rather powerful when it comes to math channels. We only have 2 math channels, unfortunately, but those math channels, each of them can be used for quite powerful type of functions. I don't know if there's a limit to the kind of complexity. I think there's a limit to 26 characters that you can use to build a function out of. But altogether we got a powerful type of math functionality here, even though if we can just produce 2 rays at the same time. Oh, there was one more thing I was originally struggling with, and that was the following. If I go to a math function and I'm going to use the formula editor, and I'm going to use one of these functions that would normally require additional parameters, for example, iris here on channel 2, and I will add to that averaging on channel 4. Doesn't matter whether this makes any sense or so. But where are the parameters? For iris I need to somehow specify the number of bits, and for averages I need to specify the count number for which averages are done. So you don't get to select that here as you do in some other devices, as I'll show you in a moment in the PicoScope. But what actually happens, you just make the formula, you don't look at any of that, you start to execute the formula, and then here in the menu you get the average numbering and the enhanced bit. So for all the parts of the formula that and there will be more here if you add more things that needed parameters, etc. So this is added here in the menu after you actually activated the math function. I only found out about this after a while. I was really struggling where I should be setting my parameters. Going to take a look now at the math function of the key side. Again, I got the same two input channels. We got a math button over here, and quite interestingly we got our own set of physical buttons here for magnitude and positioning on the screen. A nice little touch here. But let's look at how powerful or not powerful these math functions are. Well, they're relatively limited. We got a couple of regular operators. We can start the FFT function from here. Oh, this is not a touch screen, sorry about that. And there's a low pass filter. That is quite nice. The low pass filter can be set basically to any value here. One of the things, it's a small touch, but what I like about this unit is the way it deals with units. Actually, I said it properly. I'm adding now two voltages together, and it's showing me that the math function has, it shows the math function here, it has a scale of 5 volts. But now suppose that I'm adding volts to current. So I'm going to put here the second channel here on current. I'm going to go back here to the math function, and it will show me the scale is 5U, and U stands for undefined unit because I'm making a strange combination. The Siglent also does that, I think. The Roden and Swartz, we always have to set our unit ourselves. He does not automatically take a unit, but the key side and the Siglent, even in a more advanced way, choose your unit. So it can also be voltage square or whatever, you know, the result of your calculation is. Yeah, so we apparently got only one math channel. I think that's the most proper way to say it. We can only show one at a time. It's slightly more advanced because with function here we can also go to this GT internal, and that basically allows us to stack a low pass filter or FFT operation on the result of an operator. So if you want to call that with a little bit of fantasy, 2 math channels, you can do that. So there's a little functionality here hidden in there, but I think it's more fair to say that we got one single math channel. This is really very basic in terms of functionality. Now, finally the PicoScope, and the reason I've been adding it to this comparison, before I looked only at 3 devices, is that it is actually very interesting in terms of math functions. So again, I created 2 input functions here. I'm going to start the math channels here, and you can already see here, I already configured one math channel, is currently inactive. I'm going to activate it, change about the scale. I can just take it up here and scale it. It's a division function, so I get some extremes to be seen here. So adding new type of mass functions here. So you always do that via the formula editor, so that is rather consistent in a sense. You start here with the input channels and basic, so channel A plus B or so that would be. But then you also got like a whole truckload of what they call scientific functions. Some of them we've seen before at other devices, like we got integral or the derivative type of things. We got normalized. We also got duty cycles. We can track frequency, so that also works really well. We got de-skewing here, in which we can basically make a time adjustment in milli or microseconds to a channel here. Also here, for example, true power, apparent power, reactive power, power factor. So they're all already there as ready-made things. So that is really impressive. These are type of trigonometric functions. I don't think I've seen in another device except having the pi as a constant. There's a category that we call buffered functions. So basically they can provide you, for example, of the average of any capture that was already done since the device was being powered on. So the whole capture memory of the device basically is being in there. We got filters, and we got quite a lot of filters. For example, also a band stop filter here. Yeah, let's just select that one. So I'm going to get rid of the A and B that I just typed here before. And here with the band stop, for example, we say it refers to channel B. We would have a low cut frequency of 500 Hertz. And we would have a high cut frequency of 900 Hertz, for example. So this is the way that you enter parameters into this equation. And even some advanced type of coupler facilities here that define the behavior of a certain cable or so in a setting. So altogether, we really got a very advanced type of thingy here. Also, the interesting thing here is that I choose an equation. Here I basically get to give a longer name to it, array color, units, and a range. That is fine. Then I've got a second one here. I can add a third one here. I can add a fourth one. And I can go on and on. I'll just take a constant. Oh no, I cannot take only a constant. Let's just take some channels. So what I can do, basically, I can go up to 8 different mass functions shown at the same time here on the screen. And at the moment I will be adding additional functions. It will basically just add another scope window once I go above, I think 8 or 12 functions to be shown. So I see a number of axes here, a number of other axes here, and then a new one basically. Suppose if I'm turning on here, let's just take a regular channel or so, and I can add math here as well. They go over here. So I really have, as far as I can see, an unlimited number of mass channels that can operate at the same time, and each of them can be very complex as well. So I would say that the PicoScope is really the champion of the mass function, both in the depth of the functionality and the number of mass channels that you can run at the same time. I'm also particularly interested to know how all these devices deal with division by zero type of situations. Because a mathematician, I think, will tell you that dividing by zero results in an undefined value. Only when you divide 0, by definition, I think the result is 0. And if you divide something by a very small number, then the outcome is going to be a very high number. And that is typically what we do not want in daily measurement type of practice. Very high numbers, like in the tenth of thousands or hundreds of thousands, are problematic because they will mask the type of waveform that we're typically interested in looking at, or even block doing our work altogether. So ideally, you would have it kept off somewhere at some point. Now, I'm going to look into all our devices, and we'll find out that actually some of them have a specific strategy to deal with it. Sometimes it's also documented, and others do not. So I'm going to look at each of my devices now and see how they deal with division by zero situations. Now let's start to look to the Roden and Schwartz. And actually we got some information on that in the user manual. And there it says for small amplitudes of the second source, the result increases quickly. If the second source crosses 0, the result will be a range of plus infinitive to minus infinitive. In this case, instead of 0 volt, the calculation function uses the value of the least significant bit that the second source represents. Okay, so that's interesting. So it should take a low value rather than a 0 value. So I got the a signal coming here, made by a signal generator. Channel 1 is a sine wave, channel 2 is a triangle wave, and at some point channel 2 will cross through 0. So I'm dividing channel 1 by channel 2, so at the 0 crossings of the green trace, we should see how the device deals with the division calculation. Now I configured the mathematics here. Let me turn them on. So I'm dividing channel 1 by channel 2. All right. So what I'm getting here, I'm getting some value here on the screen. I'm at 200 per division. This is a dimensionless value. I'm dividing a voltage by a voltage, so it should be just a number. So I said that. But I have I'm not sure exactly how far it goes, so I configured a measurement here on my indicator here. And what I'm getting, it says it's clipping. It says VPP clipping. This is, by the way, one thing I don't like about the Roden and Schwartz scope, that if you do peak-peak measurement, it always says voltage peak-peak, even if I'm in a current or I'm in a dimensionless type of thing. But that's the way it behaves. Too bad. Other scopes do that better, I think. But it's clipping here. So it says it does something with the least significant bit. So I could try to see to go to high resolution mode where it artificially creates a higher thing. Whoa. Let's see that. So we actually get something that gets out of the screen. It's nobody in the screen. And I still have a value of 13,000. Yeah, so it might be that this high resolution is 16-bit, and then we should be able to calculate the dynamic range of 16-bit and see exactly where we are getting in that dynamic range with the least significant bit. But I'm not totally satisfied with the way that this device is behaving in terms of yeah, in terms of dealing with dividing by 0. It's still not very practical, at least if I understand everything properly. Let's see how the Siglent deals with it. And in the manual there is no information about its strategy when it comes to divide by 0. So we'll just have to find out what we get to see. So I created the same, using the same waveform, I created the same math. And yeah, I get to see very high values. And let me see here, I'm trying, this is the smallest I can get, it is 10,000 per division. Again, a dimensionless value as it should be, but it still goes out of the picture here. I cannot get it any smaller. I also created a measurement here that should show me the function, and it's clipping. We see it in this little symbol here, and it's clipping at higher than 85,000. But it's above the 85,000, so it doesn't deal well with divide by 0 at all. And in case that we're interested, would it have something to do with the number of bits or acquisition like it does in the some of the other scopes? I can put it to 8 bit, I can put it to 10 bits. No, there's no difference at all. No, unfortunate. Now to our Keysight scope, and there if we look in the manual, they do say something about that. They say in one line, the division by 0 case places holes, that is 0 values in the output waveform. Okay, interesting. So they do have a strategy. Let's see how that works out in practice. So again, the same two waveforms. Activating the math function, I get to see a nice shape and it seems to be pretty nicely kept. We have a scale of 20 per division. Again, dimensionless. So yeah, it's not that much. We can actually measure it again. I put it here and we get a ratio of or outcome value of 55. That is very nice. This scope deals by far the best until now, I think, with 0 division, even though otherwise its math functions are quite limited. And this is really satisfactory, I would say. Okay, let's see what the PicoScope does. There's nothing in the description about how it deals with zero, but again I'm interested in these points here. I created a mesh channel. The mesh channel is again dividing. And I see a scale 1 to -1. And if I scale it slower, it's keep on clipping here. But that's strange. I would expect it to be able to go higher, to 10 or 100 or so. I mean, if you divide by, why does it go any bigger than 1? I got a question mark there as well. Okay, curious. I don't know exactly what it is. Let's try to see with the measurement function if we can get a little bit more understanding of this. So I go to measurement, I take AB measurement, and I want to see the peak value here. And it's not showing anything here. It's not able to measure the peak here. I can try to do it within rulers and then set some of the rulers in a place where I know the wave to behave in a predictable way. Yeah, so here we basically see that peak is 0.5 between the two rulers that I selected, and again it's dimensionless. Well, this is okay. It still accepts like the negative peak. Yeah, no, and at the positive peak it goes wrong. It's not able to measure anymore. Yeah, so it's not dealing very well with division by zero issues. That might be a concern depending on the type of measurements that you want to make. And finally, that was all. I hope you found this an interesting episode and also see that all our devices are very different. It's not so much about the numbers of mask channels or the numbers of different mask functions, but it is really how it is all designed and is a particular scope able to deal with a particular type of mask challenge that you're dealing with or not. And again, I think they're often complementary in that respect. Thanks for watching and hope to see you back for another episode of Rudy's Electronics Lab.